All right, let's talk about something we use every single second of our lives, but barely ever think about: current electricity. It's this invisible force that powers pretty much our entire world. But the real story here, the amazing part, is how it's all about taking total microscopic chaos and turning it into the perfect order that lights up our lives. I mean, think about it. You walk into a room, you flip a switch, and bam, light. Instantly. We do it dozens of times a day without a second thought. But what is actually happening inside that wire? I promise you, the answer is way stranger and way more fascinating than you might think. So let's get into it. So here's our game plan. We're going to start by figuring out what this river of charge really is. Then we'll follow the wild, bumpy journey of a single electron. After that, we'll uncover the one rule that governs this entire flow, learn how to handle complex circuits, and finally, connect all the dots to see how this whole process gives us the power we can't live without.
Okay, first things first, what even is an electric current? We throw that term around all the time, but let's nail down a really clear, simple definition.
So officially, the current, which we call I in physics, is just the total amount of charge that flows past a specific point in a certain amount of time. We measure this in amperes, or amps for short. You know when you look at an appliance and it says 5 amps? That's exactly what it's talking about, how much charge is flowing through it. Probably the best way to get your head around this is to picture a river. The river's current isn't about how fast a single water molecule is moving. It's about how much water, how many gallons flow under a bridge every single second. It's the same thing in a wire. It's not about one electron, but the total amount of charge flowing past. So if current is a river of charge, how does that river actually start flowing? To see that, we've got to zoom in, way in, down to the microscopic level of one single electron. And this, right here, is where our chaos to order story really kicks off. Okay, so picture any piece of metal, like a copper wire, just sitting there. It's packed with billions and billions of free electrons. But they're not just hanging out. They are zipping around like a frantic swarm of bees. At incredible speeds, bouncing off atoms, colliding with each other. It is complete and utter chaos. And for every electron flying to the right, there's another one flying to the left. The result? The net flow is zero. Nothing's actually going anywhere. No current. But then you flip the switch. And what that does is create an electric field across the wire. Think of it like a gentle but very persistent wind blowing through that chaotic swarm of bees. It doesn't stop them from buzzing around randomly, but it makes the entire swarm slowly, collectively drift in one direction. And that tiny, almost invisible drift on top of all the chaos, that is your electric current. So take a guess. How fast do you think that drift actually is? How fast is an electron moving down the wire to power your light? Well, get this. For a typical copper wire, the average speed is a shockingly slow 1.1 millimeters per second. I'm not kidding. That's slower than a snail. Which should make you wonder about something, right? We'll come back to that paradox at the very end. So wait a minute. If this electric field is constantly pushing the electrons, why don't they just keep accelerating, going faster and faster forever? Well, remember that chaotic, bumpy journey? All those constant collisions with the atoms in the wire act like a kind of friction, constantly slowing the electrons down. This opposition to the flow has a name: resistance, and it's all explained by one of the most famous laws in physics. And here it is, Ohm's law. It's beautiful in its simplicity. It just says that the voltage, which is basically the push from the electric field, is equal to the current that you get multiplied by the resistance of the wire. So that R, the resistance, is just a number that tells you how much that material is fighting back against the flow. Now, that resistance isn't just some random value. It depends on the wire's length and thickness, sure, but most importantly, it depends on what the wire is made of. Every material has its own built-in or intrinsic property called resistivity. It's like the material's personality. It tells you, fundamentally, how much it naturally resists an electric current. And whoa, just look at the difference here. This is incredible. A conductor like copper has a super, super low resistivity. But an insulator like rubber, its resistivity is a billion times higher. The difference is just staggering. And this is exactly why our wires are made of copper on the inside to let the current flow, and covered in rubber on the outside to stop it dead in its tracks. Okay, let's put this to the test with something from your kitchen. A toaster. It works because the special wire inside, it's called nickerohm, has just the right amount of resistance to get red hot. And now, with what we know, we can actually calculate just how hot it gets.
So here's how we do it. First, we use good old Ohm's law to find the resistance of that toaster element when it's glowing hot. We know the voltage from the wall socket, we know the current it draws, easy. Then we use another formula that connects a material's resistance to its temperature. We plug in all the numbers, and there it is. The element inside your toaster reaches a blistering 847 degrees Celsius. Ohm's law is perfect for one little toaster, but what about something really complex, like the motherboard in your computer? It's a maze of different paths and components. For that, we need a couple more rules. And luckily, they're super simple. They're called Kirchhoff's rules, and they're just common sense. The junction rule basically says that at any fork in the road in a circuit, all the current that flows in has to flow back out. That's it. Charge can't just appear or disappear. And the loop rule is like going for a hike. If you start at your camp, walk up some hills and down some valleys, and end up back at the same camp, your total change in elevation has to be zero, right? It's the same with voltage in any closed loop. So we've defined current, we understand resistance, and we have the rules to map out any circuit. But why do we care about any of this? Well, it's because this controlled flow of charge is how we actually move and use energy. It's how we get power. Electrical power is just the rate at which energy is being delivered, and the formula couldn't be simpler. It's just the voltage, the push, multiplied by the current, the flow. And the answer you get is in watts, a word you see on pretty much everything we plug in. Now, this brings us to a massive real-world engineering problem. Whenever you send current through a real wire, some of that power gets lost. It turns into heat. And the amount of power you lose is equal to the current squared times the resistance. That little squared is a huge deal. For power lines stretching hundreds of miles, this wasted energy can be absolutely enormous. So how do you fix it? Well, look at that formula again. The power loss depends on the square of the current. So if you can lower the current, you dramatically lower the waste. And since power equals voltage times current, you can deliver the same amount of power by jacking up the voltage way, way high, which lets you lower the current way, way down. And that is why we have those giant transmission towers, carrying electricity at hundreds of thousands of volts. It's all to stop wasting energy as heat. Which brings us all the way back to our big paradox. We know for a fact that the individual electrons are just slowly drifting along at a millimeter per second. So why isn't there a huge delay when you flip a switch? Why does the light come on instantly? And here is the beautiful answer. It's not about one single electron making the whole journey from the switch to the bulb. The wire is already completely packed with electrons from end to end. When you flip that switch, the electric field, the signal to start moving, propagates through the wire at nearly the speed of light. That signal gets all the electrons everywhere in the wire to start drifting at the exact same time. It's like a hose that's already full of water. The instant you turn on the tap, water comes out the other end. So the next time you turn on a light or charge your phone, just take a second to remember what you're actually doing. You are commanding an invisible, microscopic river. You're transforming the random, chaotic dance of countless electrons into a perfectly orderly flow of energy. And this invisible system, it's just one of many that quietly govern our world. Makes you wonder, what other hidden forces are out there just waiting for us to understand them?